Let's look a little bit more at the complexity of this story of heat and health. In other words, how a warming world affects the evolution of the disease pathogens themselves, their abundance, their vectors, their latitudinal location, people movements, and so on. So this is a nice example of how to think about these. Some like it hotter. How fast mosquito-borne diseases spread depends in part on temperature, peaking at an optimum warmth and then declining above and below. So many ecological things have optimum temperatures, whether it's photosynthesis or spawning, reproduction, lifespan, and so on and so forth. Different combinations of diseases and vectors have different peaks carried by its usual mosquito vector. The most dangerous form of malaria peaks at 25 degrees C, which is before it used to be thought of as much warmer optimum temperature of 31 degrees C, but now new data shows that it's as low as 25 degrees C. Cool enough that climate change could increase transmission in some regions because many are going above 25 for sure from where they were. But dengue and Zika could burgeon in a warmer world. So here we are, transmission maximized here, and transmission is impossible at these low temperatures like 10 degrees C here, and the optimum temperature for certain pathogens like malaria is here. So malaria carried by the Anopheles gambiae mosquito is most transmissible at 25 degrees C. So you have pathogen, so mosquito species, Zika, Aedes aegypti, and West Nile has Culex tarsalis, and dengue has Aedes aegypti as the main vector. Same for Zika. West Nile is Culex pipiens. Plasmodium falciparum, which causes malaria, is Anopheles gambiae, and dengue is Aedes albopictus, which is natural to the US, for example, and Rift Valley fever is Aedes teniorhynchus. Wow, I can't say, I'm not a biologist, but nonetheless, dengue and Zika are carried by Aedes aegypti, thrive at a temperature of 29 degrees C. This is relative R0 is 1. It's, how many people get infected by a person that's already infected, and relative R0 is 0 here, so nobody transmits here and pretty much everybody is infectious over here in a simple way. So you can see how the warming temperatures shift, and then you have to understand how the pathogen shifts, how the vector population shifts, and how optimal transmission temperatures shift as well. So building a transmission curve, then scientists start by measuring the effect of temperature on many different traits of a specific pathogen and the mosquito species that carries it, how long the mosquito lives, for instance, and how fast the pathogen replicates in the mosquito, and the temperature dependence of both. The result is a series of curves which are mathematically combined into a single curve relating temperature to disease transmission. So here is trait 1. With raw data you have some optimum temperature curve. This is often called a Kuznets curve, where it's inverted U shape and there is an optimum and you drop off in this direction or in this direction. Trait 2 may be like a best fit curve to data. You can probably not see the dots here, but there are dots there which show data. But you take the data and don't just put a raw data curve, but do a best fit curve for trait 2 and so on to trait 8. You end up with something much narrower than what you see here, and you model it all together to figure out the transmission rates are 0, reproduction rate, let's say. Optimal temperature transmission then comes out here. So you have to combine that with the knowledge you have about each disease and then try to compute the risk now and risk with warming, because temperature dependence means warming. Of course, there are other factors like precipitation, humidity, winds, and human habitats, and so on and so forth. So let's look at another example of disease forecasting. Will fungal diseases come in front in I have trouble reading. It's post-lunch. I'm maybe a little bit sleepy. Will fungal diseases come in from the cold? It came as a nasty surprise when Candida auris suddenly started to cause deadly infections in 2011. The East that Candida auris was resistant to major classes of drugs and killed more than 1/3 of known patients who developed invasive infections. Even more surprising, Candida auris infections had apparently emerged simultaneously around the world. There was just no good explanation, says Arturo Casadeval, a microbiologist at the Johns Hopkins Bloomberg School of Public Health. Why should a fungus that is known to medicine all of a sudden appear in 3 continents at the same time? Of course, people move around, so you don't know how other factors played in. Casadeval had a hypothesis ready to go. Climate change, he said. In a 2010 paper in MBio, he and Monica Garcia Solace maybe, then at Yeshiva University, laid out a simple argument. Humans are largely protected from fungal infections by their high body temperature, which slows fungal growth, but as the climate heats up, this thermal barrier could erode as fungi in the environment adapt to higher temperatures. So ambient temperatures go up, they adapt to higher temperatures, then your body temperatures become okay for them to explode inside you. That happened with C. auris, Casadeval now says, and the same thing might be expected of other fungal diseases. For now, he says it's just a hypothesis, but in 2021 C. auris was found in the environment on an island in the Indian Ocean. The discovery suggested the infectious strain could have originated in the soil, not an animal host. These environmental samples grew poorly at body temperature, suggesting it took an evolutionary leap, perhaps propelled by climate change, for the fungus to turn deadly to humans. Directly from the soil, growing with climate change, warming, and being able to grow in human body at human body temperatures. What is the story then? Communicating all this complexity and uncertainty is challenging. Broad and easily understood statements such as mosquito-borne pathogens will thrive in a warming world can be seductive but misleading, Carlson acknowledges, yet okay, so that's what Carlson says, that it's seductive but can be misleading, yet conveying the nuances that climate change may end up causing more malaria in some places and less in others risks blurring the urgent message that climate change is a threat to public health. I don't think the science is getting walked back, Carlson says. I think that there is this impossibly high rhetorical bar that we have created for what the science is supposed to look like for it to be a dramatic health impact. So again, I would just say end justifies the means approach can be deadly if we lose credibility, like we'll be then like politicians that people just don't trust, right? Just a few weeks after Carlson's radio interview, the next communication challenge arose. Another locally transmitted malaria case was reported in the United States, but this time in Maryland, which had not seen such cases in 40 years. I mean, that is just really weird, Murdoch says. Still, climate change probably isn't behind this malarial threat, at least not yet. I wanted to include this because you usually hear, sorry, I don't know why I took it off while I was speaking. You usually hear that it's easier to say, yes, climate change is making things work. So when 2024 sees an outbreak of dengue across the world, especially in the Americas, then is it warming? 2023 was very warm, so is that directly related to that, or is the warming also associated with people movements or food movement and mosquito movement? We don't know. So complicated stories need to be told, but does that mean we simplify them? Does that mean we just not bother with the nuances of the science or the complications of the science and just say, yes, climate change is going to make dengue everywhere worse, malaria worse, and so on? Or do we need to say, you know, so Computing the risk is one thing, taking actions to reduce the risk, mitigating the risk is another thing, telling the science is another thing. So if climate change is a cause for many things, then the action items on adaptation and mitigation can go by themselves with the climate change, and the health risk factors need to be superposed on top, but carefully separating human factors and people movement and climate change. Very complicated, but yet it's necessary that we do it correctly and not sacrifice the science, right? So I will leave it there and see you in another topic in the next podcast.